Hello AP Chemistry and welcome to 17.3 acid-base titrations, where in the first video we talked about how to interpret a strong acid or strong base titration, which all the same characteristics, right? Just flipped in terms of what kind of pH we're looking at the beginning versus the end, right? Now we're going to talk about a weak acid titration, and we're going to talk about the key characteristics here and then compare them to what we talked about previously. So in this particular titration, we have 50 mils of this being titrated with this, right? So this is what's in our burette, right? And this is what's in our beaker, okay? Now, if we take a look at our titration curve, right, let's look at the same key points, right? So first we have this initial pH. This initial pH, wrong color, is still determined by just what's present at the beginning, meaning this is just my CH3COOH aqueous, right? Now, this differs from a strong acid in that it is not completely dissociated, yes? Because it's not completely dissociated, right, the pH reflects the fact that we are looking at a weaker acid with a lower initial hydronium ion concentration, yes? That's what we're looking at, which is why we have a higher initial pH, which can be one of the points of reference, right, if we're trying to compare two titration curves, and decide if one is a strong acid versus one is a weak acid, right? Now, obviously, that initial pH is also going to vary based on the concentration, right? For example, if we had like 17.4 molar acetic acid versus, 1 times 10 to the negative third molar HCl, right? Concentration matters for the hydronium ion concentration also. But if they're equimolar, right, a weak acid is going to have a higher starting pH, okay? Then if we move along, right, let's talk about on the way, right? So on the way up, right, as we are adding 10, 20, 30, 40, right, we have the same scenario, right, where at that point, right, the thing we are adding, which in this case is NaOH, right, is never present in excess, right, in that it is limiting, it is added, it completely reacts, right, with my acid until we reach that equivalence point, right? We're going to come back and discuss that middle point a little bit further, right? But we reach the equivalence point, where at the equivalence point, the moles of NaOH added are equal to the moles of acetic acid originally present, right? And for some reason we did not write a reaction, so let's go ahead and do that really quickly, right? So CH3COOH plus NaOH gives us H2O plus NaCH3COO aqueous, right? So in terms of what's present at this equivalence point, all that's present are my products, right? So we have H2O and CH3COO Na, right? So then, now, at first we might puzzle at the fact that our pH is not at 7, because if the moles are equal, why wouldn't it be at 7? And then you would say, that's right, because we are talking about a weak acid, right? Acetic acid is a weak acid, which means that acetate ion is, ding, 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 a weak base, yes? Acetic acid is a weak acid, which means that its conjugate base has a tendency to abstract protons from water, leaving hydroxide ions behind, leading to a pH that is basic, right, for my overall solution, right? So here, right, what's the same, right, is that only products remain at the equivalence point, right? But now the characteristics of those products are such that they affect the pH, which it didn't before, okay? And then this part after is the same as before, because here we're just talking about excess titrant, which in this case is excess NaOH, right? Now, the other thing that makes a weak titration different and unique is everything that happens from the initial up to here, right? So first you'll see, right, if we look at that other one, right, it's flat here, right? As in it's linear, yes? It can be plotted as linear from that initial pH up until we reach that inflection point where it starts to go up, right? That's not true on this weak acid titration, right? You'll see that there's actually this part here that goes up first before we reach this part that might be considered linear, right? And then the next inflection point, right? This first inflection point up here is due to the fact that there is very little hydronium ion present at the beginning, right? So as we add that first little bit of base, basically we're neutralizing all the hydronium present, right? So we get a relatively large initial change in pH, yes? a relatively large initial change in pH, right? Which is why there's that inflection there, right? And then we get this part here that might be considered linear, right? And this part is known as the, right, buffer region, which does not exist, okay? Let's be crystal clear. Does not exist in a strong acid or strong base titration because, right, we don't have the appropriate species present for it to be a thing, right? But if we think back to what one of the ways of making a buffer, right, is to do a partial neutralization, right? So here we have, at the initial point, we have all acid. Here we have no acid, but on the way in between, we have partially neutralized acid, right? Which means that in the solution itself, we have acetic acid, and we are producing acetate ion. Yes, does that make sense? So that space in between is called the buffer region, right? Now, key point here, right, of super importance, right? 50 milliliters is the volume that marks our equivalence point, yes? Which means that 25, and if we trace this up right here, would mark our half equivalence point, yes? If 50 is our equivalence point, right, then 25 marks our half equivalence point, okay? Now, the half equivalence point is where what? What's true there? Right. At the half equivalence point, this is equal to this, yes? At the half equivalence point, because half equivalence means we've neutralized half of it, yes? Half of my original acetic acid concentration is gone, and it has been converted to acetate, right? Which means this criteria is met at the half equivalence point, which then means that this becomes significant because this, on my y-axis, is, ding, 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 pKa, because pH equals pKa when the concentration of HA equals A minus, right? Throw back to what we talked about in chapter 16, yes? Okay, maybe it was the last section because these videos just keep going on and on. But anyway, pH equals pKa when HA concentration equals A minus concentration, right? Which is why weak acid titration curves are super important because they give us information about what kind of acid we are looking at and can be actually used to identify an acid, right? Based on the pKa, right? Make sense? Good? All right. Next up. Oh, and then as a point of reference, I was asking what would it look like if we did 50 mils of 0.1 molar? How would they be the same or different, right? Again, the equivalence point would happen at 50 mils on the X, but the Y would look different, right? It would happen at pH 7 in terms of the equivalence point, right? And we wouldn't get quite so many inflection points on the front end. Yes, does that make sense? It would look like that first thing we did. All right, next up, titration math. So this goes back to some of the math from chapter 16 when we talked about weak acids, right? In that, if we're going to do something to the weak acid, first we have to figure out how much weak acid is consumed or how much is left, right? And then we have to do an equilibrium calculation to figure out what the final pH is going to be, right? Another note about some titrations, right? So this is a great diagram from your guys' book, right? That sort of, it displays a lot of information at one time. It's awesome, right? So first of all, these are all 50 ml samples of equimolar acid, yes? So equal volume, equimolar with the same base, yes? And you'll see, right, key things to note, right? Equivalence point happens at 50 mils for all of them, right? Because that makes sense, right? Because that's where the moles of added base equal the moles of acid initially present, always, right? What changes, though, is the shape of the curve and the y for that point, yes? As in, on the y, it's going to vary depending on the strength of the acid, right? So for our strong acid, right, this point right here, you'll see that that's approximately 7, right, if we drag that across our y-axis, right? But the weaker my acid gets, right, the higher and higher that pH gets, because the weaker my acid, the stronger or the more basic its conjugate base is, yes? The weaker my acid, the more basic its conjugate is, right? Which is why these pHs, right, I mean, by the time we're up here, we're up to something over 10 for the pH at the equivalence point, right? And again, at the equivalence point, that pH is based on the conjugate base of the weak acid because that's what's left in the solution, right? You'll also note that the amount of rise here varies, right? The weaker my acid gets, the smaller that window gets for catching the equivalence point, right? Which means that it gets harder and harder to do a titration well, okay? You'll also see that this inflection, this first inflection here, right, gets to be a steeper rise because, again, that happens because there's so little hydronium present, right? So this inflection point, as we neutralize that a bunch of that hydronium that's initially present, right? And then we get, again, that linear part, that's our buffer region, right? And then we get that next inflection over there. All right. Next up, polyprotic acid titrations, right? So here, right, obviously, if you're ever given a titration curve that looks like this, clearly, I hope you would be like, oh, that looks funny, but then you'd be like, oh, well, it's just like 2 titrations, which would mean that it's a polyprotic acid, right? In that anytime we have this rise right here, right, that's indicative of an equivalence point, right? And then if we have another rise, that would be another equivalence point, which means that we've deprotonated this thing 2 times, right? And that's all we would be able to know, right? If it didn't tell us all this stuff up here, all we would know is that it was something that got deprotonated once and got deprotonated again, right? And so it had at least 2 acidic protons, right? That's all we could decipher without some extra information, all right? But it's the same principle we talked about before. All right, thank you for listening. Be good, stay tuned, and we will do so much practice.